All right, continue to apply Newton's universal law of gravitation. The difference here is we're going to be finding a net gravitational force due to multiple masses. First of all, and I pulled this directly from your textbook because I wanted you to see it. This is a laughable diagram of the moon, the earth, and the sun. It's so bad on so many levels. First of all, the scales are way off on the size of these objects. And according to this diagram, the sun is just as close to the earth as the moon is to the earth. We'd just be a little ball of ash floating through the universe if that were the case. So this is horribly drawn. I mean, look at this distance. This is in the neighborhood of 10 to the 8 meters, and this is in the neighborhood of 10 to the 11 meters. We call that an order of magnitude. The distance between the sun and the earth is in the order of 10 to the 3 times greater in magnitude than the distance between the earth and the moon. The other issue is the actual size of the sun. Okay? The radius of the sun compared to the radius of the earth is about 110 times. And if you take a look at this, which means the diameter is 110 times. If you take a look at this, they're drawing the sun about twice the size. Should be 110 times the size. So that's an issue. The radius of the earth compared to the moon is about 4. This one's not bad because when you take a look at the size of this moon and you put it on the earth, it's better, you know. But the moon should be half as big as what's drawn, and the sun compared to the earth should be about 500 times, no, about 50 times larger. So this is all out of whack. The distance between the sun and the earth compared to earth and the moon is 390. So this distance, whatever it is, on your handout and in your textbook, if you multiply that by 390, that should be where the sun is drawn. I'm just pointing out the discrepancies here between all of this. If the moon was the size of a small marble, then the earth would be the size of a billiard ball. You know what a marble is, right? A small marble, not a jumbo marble, a small marble. And a billiard ball or a pool ball would be about the size of the earth. You'd draw, or you'd put the marble about 3.6 meters away from the pool ball. So the marble would be here. The billiard ball would be here. The sun would be a sphere of diameter 6.5 meters. 6 meters is from this wall to here. So you'd have the sun with a sphere that big, and it wouldn't be in this room. You'd need to put it, I got to check these numbers. For some reason I'm suspect on one of these. It would be 1.4 kilometers away. So this diagram is just nonsense. Okay, what are we asked to find in this question? We are asked to determine when they are in this relative position, because these objects move around through space, what is the net gravitational force exerted on the moon by the earth and by the sun? So is the moon attracted to the earth? Yes, there is a force of gravitational attraction pulling the moon in our diagram to the right. Is the moon attracted to the sun? Yes. Newton's universal law of gravitation says any two masses are attracted. I hope you're not going to be led to the belief that because the moon is between, or the earth is between the moon and the sun, that the earth somehow blocks the gravitational force of attraction between the moon and the sun. If that were the case, then all I would have to do is just slip this under my feet to block the force of gravity between me and the earth. It doesn't work that way. Gravity extends through things. What this means is there are two forces pulling the moon to the right. One of them is the force of gravity due to the attraction of the moon and the earth. One of them is the force of gravity due to the attraction between the moon and the sun. We can calculate both of those. Okay? When we calculate the force of gravity pulling the moon to the earth, we're going to ignore the sun. It's got nothing to do with anything at that point. When we calculate the force of gravity pulling the moon and the sun together, which is the one pulling the moon to the right due to the sun, we can ignore the earth. So these are easy calculations. After that lesson on Friday and going through all those questions we did from Friday's lesson, we just have to take this g, 6.67 times 10 to the negative 11, multiplied by the mass of the moon, 7.35 times 10 to the 22, multiplied by the mass of the earth, 5.97 times 10 to the 24, and divide by the distance between them squared, which is given in the question as 3.84 times 10 to the 8 meters. And we're going to square that. Can you look back? Was this the mass of the moon given in that question we did on the previous page? I thought it was different.
It was 7.36.
Oh, okay, so slightly different. Okay. And we can calculate that. Well, we might as well calculate it. We've written all this work down. What do we have? The universal constant times the mass of the moon times the mass of the earth over the distance between the centers of the two bodies squared. I'm getting about 1.98 times 10 to the 20. I feel as though we calculated that, right? That was that actual question before. 1.98 times 10 to the 20 newtons. And then what we have to do is do the same thing for the force between the moon and the sun. So the moon's mass times the sun's mass, which is just gargantuan, divided by the distance between them squared, which would be 3.84 times 10 to the 8 plus 1.5 times 10 to the 11. Right? I mean, look at the diagram. The distance between them is not given to you as a direct number. The distance between the moon and the sun needs to be determined by adding those two numbers together. Again, a case where we do need a set of brackets there. I mean, you could make the argument that 10 to the 8 meters compared to 10 to the 11 is not that big of a deal. But we need to add it. It is going to change the answer. Okay, double check everything. G times M over R, which is the sum of those two numbers in brackets, squared. Looks okay. So 4.3 times 10 to the 20. This is a case where the large mass of the sun far overcomes any extra distance. I mean, 10 to the 30, you can't even conceive of what number that is. It's huge. So now I want to find the net force acting on the moon. What do I do with these two forces? Well, I add them together. But if I want to now kind of retroactively go back and talk, did we not get that number?
I mean, I am getting that number, but I'm getting to the 21.
Is anybody else getting to the 21? Check your exponents, Ephraim. Since you're off by one exponent, I'm guessing that you put a 23 either here or a 31 here.
Got 11, 8, 30.
Oh, just a second. Let's go back. Where'd you see that 11? Just show me on your calculator. Okay.
30.
Yeah. Keep going, keep going.
And got 22, negative 11.
Okay, well, there you go. Look what you did. You went 7.35, and then you said times 10, and then you went E. Okay, this has not come up yet, but I don't know if you've been doing that all along, and you just this time it happened. Let me finish this question, then I want to go back and talk about that, okay? So what do we do with these two forces to find the net force? We add them. So as I said, retroactively, since forces are vectors, I better go back and talk about the directions of these. And these are both in our diagram towards the right. So how do we add vectors that are in the same direction? We just add the numbers. Right? They're not competing, they're contributing to each other. So the net force will be, I'm going to be a little liberal with my rounding here. The net force is going to be 6.3 times 10 to the 20 newtons. You know, in our diagram to the right. Are we in agreement on that number when you add those together? Okay. Ephraim, I want to share what you did with everybody else because somebody else might do it. And I think you did it by accident because you saw it right away. But when you enter something like 7.35 times 10 to the 22 in your calculator, when you go 7.35 E22, and never write that on paper. On paper, you write times 10 raised to. That's what you enter, not that. And I know, because you didn't put it elsewhere, this was just one of those things where your brain did it. I know that you wouldn't be doing it elsewhere, but there is a 10 in the E. So if you ever do enter times 10 E22, this is 10 times 10 to the 22. It's actually 10 to the 23. Okay. Anyway, we solved the mystery. Okay. Let's take a look at the next question. I'm just going to go past all of this. So example number 2 gives you 3 masses in a line. They are not celestial masses. They're quite small, hundreds of kilograms. The question says, what is the net gravitational force on B due to the other 2 masses? So what we need to do here is find the gravitational force on B by A, and we need to determine the gravitational force on B by C. I want to go back and show something to you because I neglected to do this. When I drew these 2 arrows, these 2 vectors here, I intentionally just drew them and kind of walked away from them because we had no idea, based on these distances and masses, which would be greater. But it turns out that this one is the force of attraction of the moon to the sun. It's a little bit more than 2 times as great. You want to say something, Ephraim?
Well, if the force of gravity from the sun is so much bigger than the force of gravity from the Earth, then why does it rotate around the Earth instead of the sun?
Because the Earth rotates around the sun, revolves around the sun. And given the scale, it's a great question. What Ephraim is asking is, why isn't the moon in orbit around the sun if the force of gravity is so much greater? Given the scale of things and what I talked about before, the moon and the Earth together are in a collective orbit around the sun. That huge force of gravity acting on the moon, there's also a huge force of gravity acting on the Earth. So both of these collectively together are forced incredibly, with an incredible force towards the sun. And that accounts for the fact that they move around the sun in an orbit. I don't know how else to answer it. Nobody's ever asked that, and it's a really good question. I will answer it this way. It is in orbit around the sun. It's just that as it's going around the sun, it's doing these little spirally kind of things around the Earth as the Earth is going around the sun as well. It's complicated. You know, this is just a snapshot in time, by the way, right? So at some point in time, the moon is below the Earth on this diagram. And now you have it being pulled towards the sun and being pulled up towards the Earth. So I will answer it by saying the moon is in orbit around the sun. It's just also in a smaller orbit around the Earth at the same time. You're satisfied with that? Okay. That would be my hypothesis. I have to do some calculations, but just first glance, that seems like a reasonable explanation. Okay. So getting back to this then, what is the direction of the force on B by A? We're asked for the net force, this is really important, on B. So we're considering the forces on B. Well, B is forced this way because it is attracted to A due to a force of gravity between the two. B is also forced this way towards C. Do you understand, and I kind of alluded to this in the previous question, or maybe in one of the ones we went over from homework, it's not an easy task to decide which one is greater. On the one hand, the mass of C is over twice as great as the mass of A. And that, in my mind, says, well, you know what then? This is going to be twice the force. But the distance is a little bit more. I don't think that little bit more distance is enough to account for that extra mass. I think when we do the calculations, I think that we are going to have the mass on the right that I've drawn greater. But let's calculate them. What is that doing there? There we go. Let's calculate them. And I'm just going to do this on my calculator. The force of gravity between B and A will be the force on B by A. So it will be the universal constant multiplied by 380 kilograms multiplied by 270 kilograms divided by 4.5 squared. And I get, a little tiny force of gravity. Of course it's going to be tiny because these are tiny masses. I get 3.38 times 10 to the negative 7. And when I do the same thing for the force of gravity between B and C, it's 270 times 840, I think. And instead of being divided by 4.5, it's divided by 5.0. Yeah. It's not twice as great, but it's significantly larger. 6.05 times 10 to the negative 7. So we need to add these forces, don't we? That's not a question. We need to add those forces. The question becomes, how do you add a force that is left to a force that is right? It's a huge thing in physics 30. You do this with charged objects. Well, the answer is you subtract the larger magnitude minus the smaller magnitude, and then the answer is in the direction of the larger magnitude. So we have to subtract those. We add the forces by subtracting the magnitudes. And you get, you're going to have to help me out here, by confirming that you get approximately 2.67 times 10 to the negative 7 newtons, and that will be to the right. I don't want to push things here. Let's just slow down a bit. Any questions with the second example? Okay. So let's take a look at the third and what I hope is the final example. Yeah. And my plan is to set this up for you and assign for you the task of completing this example for tomorrow. In this particular question, you're asked to determine the magnitude and direction of the net gravitational force on the 45 kilogram mass. In other words, you're asked to determine the gravitational force on it. A force is a vector, so magnitude and direction are both in there. You start by drawing a free body diagram showing the forces acting on the mass that we're asked about. What is the net force acting on this mass? Are your numbers all the same? Let's just start there. Okay. Well, we will have a force pulling this to the left. And we will have a force pulling this down. And I'm going to go out on a limb and say the force pulling it down towards the bottom mass will be smaller than the force pulling it to the left because of the 35 kilogram mass. Well, it might be close. That's my hypothesis. I think what you need to do to determine that is to calculate them. Kind of like when we're doing those complicated ramp inclined plane problems, you calculate all the forces so you know what your diagram should look like. Yep.
Can you just do like a tip to tail?
After you find them, yes. But I want to point something out here, that there's a misconception here that I find some students using. So again, I'm not saying that's the relative size of the vectors, but there are vectors that look like that, right? And that this gray vector is the force of gravity on B by, oh no, B. Let's do this. Let's just make my life a little bit easier, please. Did you have letters on yours? Okay, just label ABC. Then I can say the force of gravity on B by C, and this will be the force of gravity on B by A, right? And what Sam has asked is, so do we just do a tip-to-tail thing? And the answer is yes, but you need to understand that what I'm saying yes to has nothing to do with the triangle that's formed by these positions. It's got nothing to do with that triangle connecting those blue spheres. What it has to do with is that diagram, right? And some people think they can just connect these blue spheres to find an angle and find an angle in the triangle. That's not it. You have to calculate those two forces, then draw them tip to tail so you can find the hypotenuse and the angle, and we're back to well, early on in the previous unit, draw your horizontal first, then your vertical, and then you have to find that. Capiche? That's your assignment. That's your task for tomorrow. I want everybody to complete that example. And I also want you to have a great day, and I will see you later.